So this morning, the session right before lunch, we talked about, we had Spatial Data Mining 1. We very strategically named them this way to reinforce the idea that 1 came before 2. If you're already familiar with hotspot analysis and the way that the GEDIS or GI star statistic works and the way that the cluster and outlier analysis tool works, then 1 really, it would have been a refresher anyway. But we are going to rely just a little bit on that. We're not going to get too much into the details of those statistics. We're going to talk much more about the way that they work in kind of a space-time context. So if you're feeling a little bit lost, certainly stick around and just know that there's resources that can kind of fill in some of the gaps you're noticing if you go to our resources page, which we'll point you to at the end. Okay, so what we're going to talk about is space-time pattern mining and space-time analysis. In general, the space-time pattern mining tools are a relatively new toolbox in ArcGIS. And we have a number of tools, Create Spacetime Cube, Emerging Hotspot Analysis, Local Outlier Analysis, and a couple of tools for visualization that we're going to talk about today. We're also going to talk about a new add-in that we've been working on that helps you visualize your Spacetime Cube, which we think is pretty cool, and you'll be able to download as well as soon as Pro 1.3 comes out. So I'm Lauren Bennett. This is my colleague Flora Vale. We are both on the spatial analysis team, and we work on the tools that you're going to be seeing today. So we will just get started. I'll give you a little sneak peek into who we are. We're kind of big nerds. This is an actual, did I Instagram this picture? Yeah. So one of the perks of working at Esri and being particularly at the Redlands campus, which is our headquarters, is that occasionally Waldo Tobler gives a lecture in the afternoon, and you get to go and hang out and listen to Waldo Tobler talk about the first law of geography, which was pretty amazing, and we were very excited. Actually, we were so excited that we got there like half an hour early because we were sure that like the whole auditorium would be totally full. And that did not happen. Like, there's plenty of people there, but it wasn't like standing room only. But we were like up in the front waiting for half an hour. This is when we took this picture. Anyway, so the reason I'm showing you this is because actually these tools have at their foundation Waldo Tobler's first law of geography, right? This idea that everything is related to everything else, but near things are more related than distant things. And when I was at the end of his lecture, I'm in the middle of working on my dissertation, and I'm kind of talking about space-time pattern mining as part of my work. And I asked him, and one of the things he talked about was the fact that when he wrote the paper, I think it was a 1970s paper, where he had this quote. He certainly, he didn't talk about it like, this is my first law of geography. It was just a line in his paper that became Tobler's first law of geography, right? And so I asked, if you knew then what you know now, how would you change it? Would you do anything differently? Would it still be exactly this? And what he said was, I would change it, and it would say that everything is related to everything else, but near and recent things are more related than distant things. And he didn't even know that he was about to like blow my whole mind and like totally set the stage for the work that we were doing and the things that I want to write about in my dissertation. But what he was saying was, I forgot time. Like, I didn't incorporate time in the first law of geography, but it is super important. My definition of near, or if I were him, I would say, well, what I really meant with the word near was near in space and time, because near means lots of things, right? Of course, he always meant recent. He just didn't say it explicitly. So that's basically the idea behind the space-time pattern mining tools. It's this extension of Tobler's law, that things that are more related in space, things that are closer together in space and time are more related than things that are far apart in space and time. And so that's a really important kind of, I think, foundation for what we're going to do today, because everything that is within these tools kind of has that at their foundation. So the first thing we're going to do is set the scene, because we're going to use one analysis, one set of data to kind of carry over through the whole analysis, and Flora is going to give us a peek at that data.
Okay. Here we have some water usage data for different farms in Merced County, California. And we actually are just looking at water usage in August. Because if we were, so we have, what is it, do we have 12 years?
12 years.
12 years of data. And so we could potentially look at every month over the 12 years. But since we're going to be analyzing this over space and time, if we looked at every month, we would kind of see that cycle, right? Like we were probably going to see, we're always going to expect to have more water used in the summertime. So by singling out just August, we can look at, has water usage changed over August's? So we can keep the summertime consistent and see how that has changed over space and time. So I have these point data, and I'm looking at this as graduated symbols. So the bigger ones have more water usage, and we might be able to look at this and get a sense of how the water usage varies over space. We could also maybe create a chart and look at how this water usage has been changing over time. So we see here that looks like in 2012 we had the most water usage in August. But we're only getting half of the story with each of these visualizations, right? So on the map, we're only getting the spatial story. In the chart, we're only getting the temporal story. And we want to understand these things at the same time. Near and recent things are more related. So I need to aggregate this data so that we can do some analysis on it. And I'm going to aggregate it into a space-time cube, into a 3D space-time cube. So I'm going to go to the Create Space-Time Cube tool, point to my features. I'll give this cube a name. So when creating your space-time cube, it's important to think about what you name this file. So I'm actually going to name that last so that we can talk about why it's important and how you should name it. The time field will be date, so it has to be a date format field. And we're going to do a time step interval of 1 year, because since we're just doing Augusts, it will bin up the whole year, and then we'll just have that August data in there. So 1 year. And for distance interval, we're going to do 1 mile. So it'll be 1 mile by 1 mile by 1 year. And then we have these summary fields here. So if this were incident data, like crime, for example, that's a common example that we use. Incident data doesn't have any summary fields usually. Incident data, it's just we're counting how many crimes happened in each bin. But for water usage, we actually want to sum up that water usage field. So I'm going to point to water usage and then choose sum. And now we also have this option, not option, but required parameter to fill empty bins. So when we have a summary statistic, we could have a situation where a bin does not end up with any data in there. When we're doing counts, like counting up how many crimes happened, if no crimes happened, that's a 0, because that's a true 0, no crimes happened. But if we end up with an empty bin for water usage, it could be a 0, it could be that no water was used, or it could be that we're missing data. And we never want to put it in a 0 when it's not a true 0, because that would skew our analysis results. So we have some options of what to do with empty bins. I'm going to choose 0, because since we're summing, it makes sense that if we get no data, that nothing happened there. And then in the slides, Lauren will explain more about the other options for filling empty bins. And then for aggregation shape type, this is a new parameter. We have the traditional fishnet grid, or now we have the option for a hexagon grid. So I'm going to, just for fun, choose hexagons. And, oh, now we need to name this. So we run these tools a lot, especially since we're testing them and work in the development team. But when you need to find this file to input to the other tool, so I'm going to create an aggregated netcdf file so that I can use this in other tools like the emerging hotspot analysis tool or the local outlier analysis tool. So I'm going to need to find this file and remember what the parameters were that I used to create this aggregation scheme to put into that tool. So I used to just write, like test 1, test 2, and then save them and never remember which one was which or So now I'm going to put water usage, and then I'm going to put 1 mile by 1 month.
Year.
Oh, I'm sorry, 1 year. And that way, hopefully, I'll be able to remember.
You might even end it with hex.
That's true.
That's a new thing we're doing these days.
Yes, good idea. All right, and I will hit run. So now I am creating a netcdf file that aggregates these points into 3D. And so it's kind of an anticlimactic tool. You run it, and then it just says completed successfully, and you don't see anything change. Nothing really happens.
But lots happens,
yes,
actually.
Lots happens. And you can already use this. I mean, I could put this into the visualize space-time in 2D. Why don't we take a look at that? We could take a look at this to see the counts. I'm sorry, the sums, and we'll look at. Wait, what would the display be? Where's them?
Trends.
Oh, right. I thought I was doing 3D. So we have some tools to visualize these netcdf files in 2D and 3D. And so one thing that I could do is just look at the trends.
And there are none.
There are none. Okay, well, there's one. We have one positive trend in this area. But when you run this, we get a report here with lots of important information. And Lauren is going to walk us through the report. Oh, sorry, that's the wrong tool.
Yep, I'm going to walk through the report that gets created when you run Create Spacetime Cube. I'm actually going to run through a lot of details about, so Flora just gave us like a whirlwind tour of the first step of our analysis. And basically, we're going to step backwards and kind of go through a bunch of the things that she did and talk about them in a little bit more depth. So we saw Flora use the Create Spacetime Cube tool. The Create Spacetime Cube tool takes those points and it aggregates them. When we look at them in a 2D map, we have the X and the Y, and that's it, and we can see that pattern. But especially with that 12 years worth of data, it was impossible to see what was going on, and especially because we're looking at essentially parcels, and we know what their water usage is, and so really they're just one on top of the other over 12 years. It's really difficult to see. So what the Create Spacetime Cube tool does is it essentially, we can think about it as we're using time as the third dimension. And that's a way that you'll often see us visualize it. You're definitely going to see us using time as the third dimension for a lot of the visuals in our slides, because it's really helpful for kind of getting your head around what the spacetime tools do. So we're using time as the third dimension, and the farther up you are from the ground, the more recently something happened in time. So the things at the ground level happen the farthest away. The things at the top are the most recent. So what Create Spacetime Cube tool does is it aggregates into this cube-like structure. And you can think about it like this. And you've got these, we know in each one of these bins, where we can see some points peeking out there, how many points happened at that space-time location, right? In space and time, we know how many points happened. We might also know the sum or the average of a set of values associated with the points that fell into that bin. So when we're creating the cube, we have some parameters that we have to think about. We have to think about what's the scale spatially that I'm going to choose. So in the case of the water usage, it was 1 mile. This is, you're essentially deciding what's the size of the grid that you want to create. If you don't choose one, we will by default pick one and we will evaluate your data. So if you give us really, really, really dense data, the grid cells will get a little bit smaller. If you give us more sparse data, they'll be a little bit bigger. You'll see that we do use your input data to decide what a good default cell size is going to be, but the best bet is definitely for you to think about what a good cell size is going to be. We also have to choose what is a good spatial scale to aggregate. So we spent a lot of time last session talking about how important it is to think about your question and to think about the scale of your analysis and how complex some of these decisions can be when you're doing a spatial analysis. Well, now we're doing a spatial and temporal analysis. And all of those complexities of space are still there, but we're adding some complexity by adding time. And if you're like us and you think, oh, well, we're just adding time, no big deal. It's just like space. It's not. It's not just like space. There's a lot of things that we have to think about that make time special, and we're going to talk about quite a few of them today. So in this case, in the example here, we have a 10 kilometer by 1 month cube, right? So each of those little bins, we call them, represents a 10 kilometer grid, 1 month high. Now, we have a couple slides that go through some vocabulary. And the reason we do this is because when we started building these tools, we found that we were having these, I don't want to call them arguments, lively discussions about how things would work. And we would be just debating back and forth about something. And then we'd realize we were in complete agreement, but we were using different words to talk about the same thing. Because this is a new kind of, is that a location? Is it a bin? Is it a cube? I mean, because that's kind of a cube inside of a cube, right? So we were just having these crazy conversations. So we had to agree on some vocabulary, and I think as a group we have to agree on some vocabulary so that we're all on the same page going through here. So the first thing is the bin. Each bin has this spatial and temporal extent. So there's also a concept of a location, and a location shares the spatial extent but comprises many temporal extents. So you'll have multiple bins at the same location. Those locations are very important because once we create a space-time cube, now that we have a location and there's multiple bins at that same location, we can say what's been going on at that location over time. We essentially at each location have time series information, right? So that enables us to do some kind of interesting time series analysis throughout the process. In emerging hotspot analysis, we take advantage of some time series analysis. We take advantage of some time series analysis for filling in empty bins. We're working on some new tools that take advantage of time series analysis, and that really all relies on this idea that a location is essentially a time series. We also have the concept of a time slice. Now, these time slices actually are in a lot of ways the way that we've always done temporal analysis in GIS. It's not like this is the first time anyone's thinking about time in GIS, right? Of course, we've been doing time for a long time. We're trying to integrate it a little bit more tightly and make the analysis methods. Traditionally, what we've done is we either block up things by space and look at just time, or we block up things by time. So one way that people have used spatial statistics for a long time to do temporal analysis is you would look at, if we were doing this water usage, we would look at just the first year and run a hotspot analysis. And then we would look at the next August and we'd run a hotspot analysis. And then we'd look at the one after that and we'd run a hotspot analysis. So we would essentially do time slice analysis one by one, which is totally valid and still very useful. But what that means is that at each time slice, we're pretending that time slice exists essentially in a vacuum. That time slice isn't related to the time slice before it, or it doesn't impact the time slice after it. It just exists completely independently of other time slices. And while that's valid, it is a different perspective to take to think of these time slices being interrelated in the context of kind of a 3D structure like this. So when we create a space-time cube, the first thing that we do, and we always do this, is we count up the points that fall in each one of the bins. Now, if you're looking at something like crime, that may be all you care about is that count. But we do that, and here we're aggregating using those counts in the cube. So just aggregating it, you can start to understand your data a little bit better when you look at it in this kind of 3D way. And you can start to visualize the patterns in your data that you wouldn't be able to see if you were just looking at the points on a map. Aggregating it, taking an immense data set and aggregating it starts to show you some patterns. Now, in addition to the counts, we also have these summary fields that you can calculate. Flora showed us the sum, but there's a number of different ways that we can do that. We have the sum, the mean, the median, the min, the max, and the standard deviation for any attribute that you want to calculate. So when we do analysis, when we use the cube, one of the important pieces, one of the things that we're doing when you run an emerging hotspot analysis, for instance, and even when we run Create Spacetime Cube, is we do trend analysis. And again, this comes back to the importance of those locations. And the trend analysis One of the statistics that we've been using for trend analysis up until now is a statistic called the Mann-Kendall statistic. And one of the requirements of basically all time series analysis is that you have a complete time series. You can't have missing values in the middle of a time series and do a time series analysis. So you can't just pluck out 2 of those bins because nothing happened there and say, okay, we'll analyze the trend. It doesn't work. So what do? We have to fill in those empty bins. So if I'm looking at water usage and there's a bin where there's been data, all of a sudden there's no data and then there continues to be data past that, I have to make a decision. What does it mean that no points fell in that bin? If I'm summing and I'm looking at water usage, it could mean I can decide that it means that it's 0. So no points fell in there, it means there was no water usage. I'm going to give them a 0. If we're talking about counts, it's a 0. No crime happened at that location at that time, right? Now, that's not always what we want to do, though. If you're thinking about, if you're creating a space-time cube looking at like home sale values, and you had home sales, and then all of a sudden you had and you were averaging the average home sale, the average home price, right? And then you get to a space-time bin, and there are no home sales. Does that mean that the average price was 0? Did the average house sell for 0 at that time? Probably not. Yeah, that would be nice. I'd buy that house. 1, please. But no, that probably isn't what we want. So there's a couple of other ways that you can think about filling in your empty bins. One of them is with spatial neighbors. So actually look at your spatial neighborhood and essentially create the average from the spatial neighbors and fill it in. We're essentially imputing values here, right? We are estimating what the value would be at that location based on spatial neighbors. You can also use space-time neighbors. So with space-time neighbors, we look both ahead and behind you and all around you, and it's essentially providing more information. It's also a smoother imputation, right? So it's going to smooth things out more because you're using more of the data surrounding you when you do the space-time neighbors. Another option is to use just your temporal neighbors. And actually, you can think about this temporal neighbor estimation like an interpolation, but over time. So if we had a point, and then we had a missing value and then another point, essentially we're just fitting a line along that time series, and wherever that line falls where you're missing a value, we use that value to fill it in. So you can think about it that way. It's fitting that line and then just throwing those values in based purely on your time series. Now you'll notice that the first 2 and the last 2 in the cube are gray here, and that's a reminder to myself and to you that if you want to use the temporal neighbor option, the first 2 bins and the last 2 bins have to have data in them because we are interpolating, we are not extrapolating. So we can't estimate the last one because there's no line past it, right? If we're interpolating between known values, so it is a requirement that you have data at the beginning and the end of that time series to fill them in. Okay, so now we get to some of the really exciting stuff about time. Okay, so everybody just relax. And just take a deep breath and try to come along with me while we talk about this time stuff, because it is a bit of a brain, it takes a shift, I think, in the way we think about things as geographers and people that think spatially. It's just a different way of thinking about our data. So just bear with me, okay? We're going to talk about this time data. So we have data that is going from March 22nd, one of my favorite people's birthdays, to April 16th, which may or may not be my birthday. And from March 22nd to April 16th, we have this beautiful data set. And the dates that our data start and end are critical in our analysis. Now, if you think about it, when we start to bin data, if I say, create a cube that's in 1-month chunks, and I did that with this data, what would happen? Where would I start? Do I start at the beginning and move forward? Then it would be March 22nd, or let's say I say a week. March 22nd, 1 week, 1 week, 1 week. What happens if it doesn't break the data up in exactly 1 week chunks? Then what happens? I'm going to have I'm going to have a bunch of time that's not represented by my data, but I'm chunking my data up that way. So where do I start? Should I start at the end and go backwards? Should I start at the beginning and go forwards? What's the right way to do it? And what are the implications of that? So you actually have to make this decision when you create a space-time cube. Our default is end time, but we'll start with start time. You have to decide where you want to start your temporal aggregation. So in this case, if we aggregate our data in this way, we have dates starting from March 22nd going to March 26th, and it keeps going, right, all the way until we get to the last time period, which starts on the 15th and goes up until but not including the 19th. So our data only goes to the 16th, but our temporal blocks go all the way through the 17th and also include all of the 18th. So now I have 2 full days that I've chunked my data into, but there is no data in my data set. So what happens is that last time period is going to look like a lot less incidents happened in the last time period. But in reality, I just wasn't collecting data past the 16th. So is that really reflective of the actual temporal pattern in my data? Probably not. So what I end up with, we think about this essentially as bias we think about this as temporal bias, because now we have a period in time that looks low, but actually just my data ended before my time period ended in the way I'm chunking it up. Now we could also do this with end time. End time, we start at the end of the data set and go the other way. So it doesn't get rid of temporal bias, it just puts it at the end. It puts it at the beginning of my data set instead of the end. Now we chose to make end time the default. And the reason that we chose to make end time the default is because oftentimes what we're most interested in what's happening now. So if I had to pick where's my bias going to be, I would put it at the beginning, not the end. Now, if I really had a choice, I would choose no bias. And so there are some ways that we can deal with that, and we actually give you a lot of information about the bias, but it is very important to think about. And so you have this option about whether you want to start at the start time or the end time. Now, when you're creating a cube, and I think thinking about the temporal bias is one of those things that becomes the trickiest. So there are some, let's think about how you would deal with that. In this case, what I would probably do is I would chunk off the last 3 days of my data, the beginning 3 days of my data set, so that if I was really set on having a 4-day interval, that my data broke up into 4-day chunks, right? If I have yearly data, if I want to analyze my data by year, but I happen to have data that goes January from 10 years ago all the way until, right, February of the current year, I'd get rid of February and January and just go till the end of the last year so that my data broke up into 1-year chunks. So it's really important that the way you're going to chunk your data is appropriate for the length of time that you have data for. That's essentially the best way to get rid of that temporal bias. So when you're creating a cube, you also have the option to use what we call a template cube. Now, template cubes are really important because sometimes you do an analysis and then you want to come back, let's say the following month, the following year, and you want to create a new cube because now you have another month or another year worth of data. But you want to make sure that you can reasonably compare the results that you already had with the new results that you get based on your new data. So you want to make sure that your grid lines up. You want to make sure that the temporal breaks line up perfectly. You essentially want to just be adding another time period into an existing cube. Or maybe you have new data that extends beyond the cube, that's okay, but you want to make sure that the grids match, and then you just add further. You don't want them to totally misalign, right? And so the template cube helps us do that kind of aligning. Now, if you give us a template cube and that template cube happens to start before any of your data, we're going to go end time, back, and fill it in. If your data, if it happens to start at the end of any of your data, we're going to go back, and see how we're acknowledging from your template cube whether that template cube was built using end time or start time. So it's going to try as hard as we can to mimic the input template cube as much as possible. Now, if you give us a template cube and the template cube extends beyond where your data exists, we will extend beyond where your data exists. So you can introduce temporal bias in that way also, right? So you really want to think about if all of a sudden you give us a template cube that goes 3 years past your data, you're going to have 3 empty years worth of data because you've given us this cube that we're trying to fill in. So you have to think about the implications of that as well. Okay, you can also give us a reference time. So this is another way to think about dealing with temporal bias. If you're really set on not dropping any of your data, you can set a reference time so at least it spreads the bias out on both sides. So if you wanted it to go in 4-day chunks, you could have 1 extra day on one side and 1 extra day on the other by choosing a reference time that would then split it up evenly that way. The reference time also ensures that if you use data sets that are slightly different, like let's say you want to compare 2 different types of crime, and one crime, the last crime happened to happen on April 16th, and another type of crime it happened to happen on April 17th. You could use a reference time to ensure that regardless of the true end time of that data set, you're using the same point from which to start the cube. And there's a lot of kind of details about how that reference time works depending on where it falls based on your data set. And all these graphics are in the documentation. So since I know everyone didn't just completely memorize all the things that I just said about these parameters, which are really fine grained about the temporal aspects of your data, they are in the documentation. Now, when we run create spacetime cube, we give you this giant report, which Flora didn't go through because that's about how small it would look on the big screen. In real life, when you're looking at it, it's actually legible, I swear, but we've enlarged it so that we can talk about it here. And this is the report that we're going to get, and we're going to talk about the pieces of the report. We tried really hard to make the report useful that comes out through the messages window so that you could use it to really understand the cube that you created. So the first thing that's worth mentioning is what Flora pointed out, which is naming your cube super important. I find this to be true in my analysis in general. I have to be really smart about how I name my output because forget about remembering what I did a week ago. I don't remember what I did yesterday. So remembering these based on the names is super a really good habit to get into. And so we have that information. We also write this paragraph, which I actually love this paragraph. I think it makes a really big, it really helps. So we tell you that we created a space-time cube that contains point counts for 2,450 locations. So when we aggregated that water usage, there were 2,450 unique locations in the cube that we created. And it's over 12 time-step intervals, which makes sense because we had 12 years worth of data and we did a yearly thing in August. Each location is 1 mile by 1 mile, spanning an area of 50 miles west to east and 49 miles north to south. So we're getting kind of a feeling for what the cube represents spatially. Each of the time step intervals is 1 year in duration, so the entire time period cover is 12 years. Of those 2,450 locations, 1,291 of them contain at least 1 point for at least 1 time step interval. So what that means, when we create the space-time cube, that 2,450, that means that's this kind of 50 by 50 grid that we created. But not every location there actually had data fall inside of it. If you remember, the kind of shape of the data was like this. So there are some locations that don't have any data in them. It's telling us that actually about 1,291 of those locations actually have data in them and are going to be included in our analysis as we move forward. These 1,291 locations have a ton of bins, of which all of them have point counts greater than 1. which is great. It means our data set actually had pretty consistent data over time. Our farms all had data over that 12-year period. And it's saying that we also do a trend on the actual, just the count. We do a trend on the count over time. So it's telling us that, which is also a good sign, that the number of points, the number of, in this case, farms, didn't change over time, because that's all it's doing. It's counting up the number in each time slice and looking at that count over time and saying there wasn't an increase or decrease in the count at each time slice over time. So right away, this like paragraph in English is kind of helpful the first couple times you create a space-time cube for getting your head around some of that vocabulary and just reminding you what we did when we created that cube. So we start by giving you the temporal extent of your input features. Well, this is also great because a lot of times you think you know your data, and then you run this and you're like, what? I don't have data in like 1914, and some crazy data feature just like totally throw off your whole analysis because it's accidentally totally misrepresented in the data set. So it's just good to have a gut check on the temporal extent. We also give you the number of time steps and the time step interval. We tell you if you chose a time step alignment that was start or end. We also give you information about the first time step and the last time step and whether or not there was temporal bias. So in this case, you'll notice that we have what we call, we have 100% temporal bias in that first time step. Now this is where we kind of debated back and forth about whether we should use this water usage data or something simpler like crime, where you'd have the crime data would be continuous. Things are happening throughout the year, right? In this case, we did August, but we said yearly, okay? So we're doing a yearly aggregation, but we actually only have data 1 month of that year. And all of the data happens on the same day. It's all August 31st, I think, of each year. So each data, for each time slice in my point data set, I had August 31st, 2000, then August 31st, 2001, August 31st, 2002. So I've done a yearly aggregation, but in each of those years, I only have 1 day worth of data. Does that make sense? I only have 1 day worth of data in each of those time slices. But that's okay. I knew I was doing that. I'm essentially using an even more complex kind of subset of my data because it makes sense for me to look at August at each year. Because of that, it's going to tell me I have temporal bias. And that's because in that first time step, it's seeing that I have only 1 day out of 365 days. Oh, there's a lot of bias, okay? Now, when you do this kind of analysis where you look at, let's say, just August, or you could do just Mondays, or you could do a weekly. You could do just Mondays and then do a 1 week time step interval. Or you could do, you could do just weekends and do a 1 week interval. So there's lots of options you have for how to break up this data and look at cyclical patterns. When you do that, it's always going to tell you have temporal bias. You just have to think about it. Was I expecting temporal bias? Oh, okay, no problem. I'm moving on. In this case, it's totally fine that we have that bias. It's just telling us about it. Now, if I was looking at crime and it told me I had 100% bias, what that would say to me is I started at the end and I went back, and let's say I was doing yearly data and it started on, okay, let me think about this. If I started on January 1st, right, and I started at the end, my last data point was January 1st of this year. And I went back a year, and then I went back another year, and then I went back another year. If my data started on December 31st, it means I'd go from January 1 to January 1 to January 1 to January 1. I'd create the last bin, and then I'd say, oh, wait, we still have more data. And so we'd create one more bin because we'd still have December 31st. It wouldn't be falling into any of those bins. Now we've created a bin at the beginning that has 1 day of data in it, one crime. So you're going to have a bottom of your cube that is completely empty of data except for this one crime. You definitely don't want that. You'd want to get rid of that December 31st so it went January 1 to January 1 to January 1 and fix your bias problem. I know it feels like we're talking a lot about this, but this is one of the most important things that you're going to think about when you're creating a space-time cube. So if it's not clicking right now, my best recommendation is to give it a try. This is 100% one of those things where until you're just like sitting there with temporal data, thinking about your own dates and your own data, it sometimes just takes a little longer to click. So definitely be thinking about the temporal bias.
And also,
Yeah.
So we recommend that you cut out those extra days to remove the bias, but when you run the tool again, it still might say that there is bias because it doesn't mean that your data is necessarily going to end up perfect.
Right.
So that's also confusing.
A little bit
sometimes
of
when you
bias,
give it a
like
try.
it'll say like 7% because maybe you truly didn't have any crimes on January 1st. That's okay. You just want to make sure that that reflects your actual data and not an artifact of the aggregation that you're doing. So we have the start time, and we have the first time step and the last time step. We also have information about the cube extent across space. We know how many rows and columns there are. We know the total number of bins in the cube. We also know the total number of locations and the total number of locations that have at least one point. So this is just kind of an artifact of the way that NetCDF works, but the NetCDF file, which is what we're using, how many of you are familiar with NetCDF? Okay, that's awesome. But it's not that large of a portion of you. We tried really hard to make it so you don't have to learn how to use this brand new data format to use these tools. We're using it because it's the best possible storage method for us to use for this space-time cube. It's like built for this kind of multi-dimensional data. But we're trying really hard to make it so that you don't have to learn anything about NetCDF. But behind the scenes, it has to be stored essentially in this kind of square. And so that's the difference here between the total number of locations and then the locations with at least 1 point. And then we also give you some information about any of the fields that you are aggregating or that you're summarizing, so you know what can happen if you have a lot of empty bins. Let's say you choose space-time neighbors, and we try to fill it in with space-time neighbors to fill in an empty bin, and you don't have enough space-time neighbors, we can't fill that bin in. And if we can't fill the bin in, the entire location has to be dropped from the analysis. There can be no locations with empty bins. So we will do our best to fill them in based on the parameter that you choose, but if we can't fill it in, we will drop that location. And we will tell you how many we dropped, and we will actually, one of the options for visualizing in 2D will allow you to look at the locations that were dropped because they couldn't be filled in, so you get a picture of where you were missing a lot of data. We'll also allow, you can also map locations where we had to estimate bins. You can actually map in 3D which bins were estimated, because if you have a whole section of your map that has a lot of estimated bins, that might be a location where you're less confident because those aren't the true values, they're the values that we've estimated based on spatial or temporal or space-time neighbors. So as a result of having excluded bins, you may have a different number of locations with values for the summarized field as you do for the counts. And then we have the percentage of the included locations with estimated bins and the percentage of the bins that were estimated. So that's another kind of way of gauging how confident you might be in the cube that you created. For each attribute, so we have count and we have any attribute that you summarize. We also do an overall trend, so that we use that same Mann-Kendall statistic, which tries to see if values are increasing or decreasing over time. We do an overall Mann-Kendall, so that's not location by location. It's for the entire cube over time. Did it increase or decrease? And we give you that information as well as part of the report that gets created when you run Create Spacetime Cube. So actually, it's funny because Create Spacetime Cube is anticlimactic. It's the aggregation part, right? But it's actually like the hard, like everyone just, okay, wait, ready? That's the hard part. Now it gets really fun. Creating the Spacetime Cube is definitely the part that requires the kind of most thoughtful introspection about your data and the time, and it's where time really starts to have a big impact on the decisions that you make. Okay, so now we've created a Spacetime Cube, and we get to actually do some awesome analysis using that Spacetime Cube. So we start The first tool that we released, when we released the Spacetime Pattern Mining Toolbox, it had just Create Spacetime Cube and Emerging Hotspot Analysis in it. So it was our first tool that worked on the cube. So we have a cube, and essentially what we're doing is we're looking at each bin and its neighbors, and we're saying, and it's not just its neighbors in space, it's also its neighbors in time, and we compare that local area, that neighborhood, to the entire study area. And we say, and we ask, is this neighborhood significantly different from the whole cube? So just like the way that the Gettisaur GI star statistic works in space, it's just also now in time. And if you are significantly higher, then if that neighborhood's significantly higher from the cube, then you're marked as a hotspot. And we go through and we do that until every bin in the space-time cube is either a hotspot or a cold spot, or it's not significant. Now, what we found when we started thinking about this analysis was that, I don't know if you remember, let's look, let me go back, I know, oh man. So it told us the total number of bins we had, right? 29,000 bins are in our space-time cube, okay? And almost 15,000 of them are being analyzed when we do this emerging hotspot analysis. So, anybody want to guess how useful it is as an individual analyst to look at 15,000 color-coded bins in 3D? And this isn't even a particularly large space-time cube. One of my colleagues on our team looked at lightning strikes across the entire Midwest. I mean, it is like a ridiculously large cube. And while it's very useful to look at it in 3D, if that was all you had, you would be completely lost. It's just too much data for an analyst to evaluate. So we knew that this would be useful, and we knew right away that we were going to have to get into this 3D space that we weren't very familiar with. But we also knew that we were not going to be happy if it was just a 3D visualization. So the actual output of emerging hotspot analysis is a 2D map. And that 2D map essentially is the categorization of each location based on its trends over time from that space-time hotspot analysis. So we can see, for instance, a location, that one that's got the red in the middle and the white around it at the top, that's what we call a new hotspot. And if you go down that location at all the bins, a new hotspot means that last time period is the first time ever it's been a hotspot. It's a hotspot analysis for the first time ever. It's a new hotspot. Or we have at the corner here, it's like pink and white speckly. That's what we call a sporadic hotspot. And if we go down the location there, we can see it's hot, then it's not, then it's hot, then it's not, and it finishes hot. So that's a sporadic hotspot. And so we have these categories that help us make sense of the results of our space-time hotspot analysis. And the truth is, and this is something that comes up a lot when we're actually talking about talking with users who are doing some really cool analysis using the space-time pattern mining tools. They'll say, well, what if maybe I only have 12 time periods and I don't want, so in order for something to be what we call a persistent hotspot that says it's been hot pretty much the entire time, we have a rule that says in order to be persistent, 90% of the time you have to have been hot. But we just picked 90% is just the number we picked to categorize it. It's just a category. We picked these categories based on having done a lot of hotspot analysis and worked with a lot of users and thinking about what would I want to know about my data in this context. But you can certainly tweak that. I mean, there's no rule that says it has to be 90%. The statistics exist in the space-time hotspot analysis. That's where the z-scores and the p-values live. Those categories are much more fluid and much more open to your interpretation. If you don't even care about a couple of those categories and you want to clump them together, So for instance, we have a category, there's persistent, intensifying, and diminishing. And you'll see we have those for hot and cold. And what that means, for all three of them, you have to have been either hot or cold at least 90% of the time. You're intensifying if your z-scores are increasing, you're diminishing if your z-scores are decreasing, and you're just persistent if there's no trend up or down. But at the end of the day, what they share in common is that all three of them have been significantly hot at least 90% of the time. So if you decide, I don't care about the trend in the z-scores, I just care that they've been hot the whole time, you can say, I'm going to mush these categories together. I'm going to make them all bright red and just call them all persistent if I want to, because that's the story I'm trying to tell to, let's say, a decision maker. So one of the things that we see a lot is that these categories are very useful to us as analysts because we want to get in and really understand the intricacies of the patterns. But when it comes to sharing the results with the decision maker, you really want to think about, am I going to completely overwhelm them with this many categories? What categories do they actually care about? What will they care about? Do they care intensifying, diminishing? Maybe, maybe not. So we worked with, if you look at the user conference videos from last year, Bex, it's a big seed company. We did an analysis with them looking at customer sales, like customer data. And at the end of the analysis, the analyst, the GIS analyst was super excited, and we were talking about it, and it's like, okay, but how are we going to make this useful to our executives? And we totally changed the color scheme. We totally grouped things together because at the end of the day, we were just trying to tell the story. And actually, in some cases, we had to flip colors because high values are red and low values are blue. But if you're talking about sales, that means high sales are going to show up as red and low sales are going to show up as blue. But aren't high sales good and low sales bad? So shouldn't low sales be red and high sales be blue? I mean, there's no right or wrong here, right? It's about what story you're trying to tell. And I think that's a really important thing to remember about these categories. Because while the underlying, the statistics behind the space-time hotspot analysis are absolutely not changeable. You can't go in and change that around. The categories are very much open to your interpretation. All right, so Flora is going to give us an example of, show us what emerging hotspot analysis looks like on that water usage data.
Okay, really quickly before I do that, I just wanted to say that this was what I was trying to show you earlier, not the 2D version. But the 2D version did confirm that we didn't have any significant trends that we saw in our report. But with just the cube, this is the aggregation. So we can kind of visualize this and see where we have the most water usage. But now we're going to use the emerging hotspot analysis tool to see if there is any clustering in water usage. So now we know where we have the most water usage, but with the hotspot analysis, we can test for, is this pattern random or is there clustering? So I'll go back to my 2D map here, and we will use that NetCDF that I created earlier as an input to the emerging hotspot analysis tool. So my nicely named water usage, 1 mile, 1 year, hex. And we could analyze just the count. In this case, it wouldn't make any sense because we're not interested in if the number of farms has changed. So that's why we created that summary variable. And we will give it a neighborhood distance. Should I just use the default here? Mm-hmm. Yeah, okay. And run. So the time step default is one time step back. It'll include one neighbor. And the neighborhood, we use the same as we do for optimized hotspot, right?
No, for Spacetime Cube, it's actually a second order Queen's case contiguity. So it's going to go 1 out and then 2 out from that central bin. So you have one bin, it's going to get all its neighbors around it, and then all of those neighbors as the default distance band.
So here we have the results condensed in 2D. So we see that we have some persistent hotspots in these areas. So they have been hotspots at least 90% of the time, and they were hotspots in the most recent time period. Pretty much all of these categories, you have to have been significant in the most recent time period, except for one, the historical hotspot and historical cold spot. Those mean that the location was significant at least 90% of the time, but not in the most recent time period. So it's still important to know about that place because it's been significant so much, but it no longer is significant as of the most recent time period. And around these persistent, we have some sporadic. So it's really actually easiest to understand this if we also look at the 3D. So like Lauren said, just looking at the 3D by itself is really not going to be very useful. And looking at the 2D by itself, you can get a lot of information out of it, but when you put them together is when you really get the most information out of your analysis results. So I'm going to use the Visualize Cube in 3D. And now that I've run the emerging hotspot analysis, my NetCDF has the z-score results written to it. So I will do display theme. Now I have the option of hot and cold spot results. When I created this value 3D visualization of the cube before running the hotspot analysis, this hot and cold spot results was not an option. I could have only looked at the value or the estimated bins. And we will run that. Turn this off. Oops. I put it into my 2D map, but I can just copy it over once it's done running. Okay. All right. So when you are visualizing things in 3D, we have some limits to the visualization because if you have a lot of data, it might take a long time to draw. And so we recommend that you come over here to under Appearance and Clear Limits so that you can see all of the bins. Otherwise, you might be missing some of them. I'm not exactly sure what the limit is, but it's something you might want to consider. So now we can compare these two maps. I'm actually going to link my views so that we can explore these together. So over here, we see that we have a persistent cold spot and a sporadic cold spot. And it's easy to understand these by looking at the 3D. So with the persistent cold spot, it's been cold pretty much all of the time, and it was cold most recently. So it's persistently cold. If it had a significant trend getting colder or getting less cold, it could have been an intensifying cold spot or a diminishing cold spot. But there was no trend in the z-score, so it's just a persistent hot spot. This one over here is a sporadic cold spot. So the most recent time period was cold, but some of them have been not significant, kind of on and off, cold or not significant. And we can take a look at another example here. This is a sporadic hot spot. Hot, not hot, hot, not hot. So using these two together is really useful in understanding these results. And like Lauren said, you might want to translate this for your decision makers. So if you just gave this 2D map, even if you gave both maps to a decision maker, they might not be, they might not understand what you mean by something like a sporadic hotspot. So you might translate that depending on your analysis question and why you ran the analysis in the first place.
So I can actually show you an example of that. One of our partners, Blue Raster, did some cool analysis using emerging hotspot analysis. And so they were looking at, oh, this is forest loss. And it's really cool because they have worldwide forest loss, very, 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 I think it's 30-meter resolution across the world. And they were looking at emerging hotspot analysis of forest loss. And so this is their preliminary results with our kind of traditional symbology. And what they did is they wanted to tell the story in a way that would be meaningful to the decision makers in this field. And so they totally changed the symbology around to essentially what they call a forest narrative. And so they changed it so that everything that was diminishing, no direction, or intensifying, they called that legacy forest change. Then they had consecutive, they mixed sporadic and oscillating together because they just didn't see that the need for that characterization, and then new became this very bright red. So they totally changed the way that these stories were told to be something that would be meaningful to the policymakers in the context of forest loss. And I just think it's a really great example of, first of all, a really interesting analysis using emerging hotspot analysis, but also the idea of the importance of thinking about who your audience is and storytelling in a meaningful way. Okay, so that is emerging hotspot analysis.
Oh, and you need to have at least 10 time steps for the emerging
Yes.
hotspot analysis, which I forgot to mention, because that comes up a lot.
Yes.
People are like, oh, I only have 6, what can I do?
No.
You can't, because we're looking at trends.
Yep, you need to have at least 10 time slices in order for the trends to work. So that is a requirement. Okay, so the next tool we're going to look at is local outlier analysis really quickly, just because it's very similar. Essentially, we're asking the question, is this bin significantly different from all the other bins? And is the neighborhood significantly different from all of the other neighborhoods, except it's in space and time? And ultimately, we do this space-time cluster and outlier analysis, which we call local outlier analysis. Now, in the same way, we tried to come up with a way that we could meaningfully kind of boil that down into a 2D map. This became a lot more complicated because there's now 4 things that a bin can be instead of just 2. It's not just hot or cold. Now you're a high-high, you're a low-low, you're a high-low, you're a low-high. And you can be any combination of those things over the time period. So it got a little complicated. So what we ended up doing was we said either a location has only ever been a high-high, it's only ever been a high-low outlier, it's only ever been a low-high outlier, it's only ever been a low-low cluster, or if it's flip-flopped at all between any of the types, then it gets this multiple types categorization. And you really have to, I think more so than even more so than emerging hotspot analysis, you really need to use both the 2D and the 3D visualizations to make sense of this output, because it really can, there are so many options here that you really have to explore it further to understand, like, what does multiple types mean? You have to dig in and see it in 3D as well. So Flora's going to show us local outlier analysis.
Okay. So I'll point to that same cube and my water usage variable and run.
Takes a little longer because of the permutations, but it's still pretty fast.
So now we have that 2D output. So the light blue areas, that means that it's definitely easier to understand with the 3D, but it means that if one of these bins is colored, it has been significant at some point. So when we say only high-high, it doesn't mean that it's always been high-high. It's just that's the only significance type it's ever been, if it had a significance type.
It could also be not significant at other points in time. It just means it was never another kind of outlier or cluster.
Right. So let's visualize this one in 3D.
Actually, instead of visualizing that one in 3D using those, why don't we visualize it in 3D using the new add-in that we've been working on? Okay, so we had these, sorry.
No, it's okay.
So we had these, those tools are great, but we knew that we could do better than these utilities. We knew all along this was essentially our only way of making it work right when we released it. And we knew we couldn't release it if we were going to make you try to figure out how to do that 3D stuff all by yourself. So we created these geoprocessing tools to make it easier. But we really want this to become something that the application just knows how to do automatically. We're not quite there yet, but the add-in is getting us one step closer. So this is an add-in. You're going to be able to download this add-in as soon as Pro 1.3 releases. We created a short URL for it, so we'll give that to you, and as soon as Pro releases, you'll be able to download it. What that means is when you download this add-in, literally all you do is double click on it, and it'll just show up as an add-in. It'll install, essentially. You'll have this add-in, and you'll be able to launch the Spacetime Cube Explorer. It is digitally signed by Esri, in case that matters to anybody, but that will hopefully help with some security issues. If you are concerned about installing some add-in, at least it will be digitally signed by Esri. So the way that the add-in works is you point to your Spacetime Cube and you choose the name of the output feature class, very similar to the way that the geoprocessing tools work. In this case, you choose to either visualize the results of your emerging hotspot analysis or local outlier analysis. Now, if that cube had 5 variables in it and you had run an emerging hotspot analysis on all 5 variables, you'd be able to look at all 5 variables kind of at the same time. In this case, we were just looking at water usage. So we'll create the layer. And up until now, it's going to feel very much like those geoprocessing tools. And it is very much like those geoprocessing tools. Except for some pretty cool things that it adds that we can do. So after we create the layer, we can point to that layer, we select it, it will see any layer that was created by the cube. So these are all layers that I created using this Explorer, and it'll find all of those layers. And then I choose a variable, and now I have a bunch of options. So to start, I might just be interested in looking at all of my data, just looking at coloring it by value. So this is saying this is the sum of the water usage, right? Over this is the sum of the water usage over time. Or I might, for instance, while still coloring by value, want to filter by value. Now when I choose to filter by value, it automatically sets up a range slider for me. And now I can go in here and start to interact with my data and look just at the highest values automatically, which I think is pretty cool. Then I could go back and let's say I want to look at my hotspot and cold spot results. So I can start to explore that. I might want to filter by significance. It'll set up a range slider for me, and I can step through and look just at various categories of significance in my cube, just looking at the highest highs, for instance. Or I might want to filter by value. So in this case, I'm actually visualizing based on the results of my hotspot analysis, but I can look just at those highest values. So these are the places that were hot, that were either hot or cold, but had pretty high values associated with them. So we can start to really explore how that analysis works. Or I could actually filter by z-score. Or I can visualize by z-score. It's only going to visualize the z-scores that are significant, either hot or cold. And I can look just at the largest z-scores. So these are essentially the hottest of the hot in terms of clusters. Now, in addition to all of the different ways I can kind of play around with filtering, although this is actually one more. Let's say I'm looking at it like this. I can also choose to filter by row or column, which is also really cool. So I can play around with this, and it's going to start to essentially peel back the rows. So it's kind of like I'm like digging into my cube and seeing inside of it, which is really fun to play around with. I mean, it's just really nice because the visualization that we're using here, which is this real world size, it's hard to see inside of the cube, and that was always one of my biggest it's the most beautiful way to visualize it, but I always complained. I'd go back and forth with the guy on the 3D team one of the guys on the 3D team who helped us build this, because this is his favorite way. But I'd say, but I can't see inside the cube. It's not useful. All I can see is what's on the outside. So this is the first thing he did, so that I would give up on visualizing them in screen space, because he hates it when I do it like this, because it's true, they're not nearly as pretty, but I can see inside of them. But it doesn't matter as much when you're able to kind of peel layers away in the way that you can. So in addition to those different kind of ways of looking at it, we also have options to play around with the time slider as well. And so we can look at a single slice and play around with looking at how the pattern has changed over time. We can look at our space-time analysis. This is essentially looking at it slice by slice, which is really powerful. Or I can do cumulative time, and then instead of it doing it one by one, it's going to essentially be stacking them up as I go along instead of turning them one on it over and over again. So we have a lot of ways to kind of play around with the data. And of course, I can also look at my local outlier analysis results. Which is what I promised I would do. And we can play around and explore this data as well and see where we have, for instance, so like this one here would show up as let's look at our local outlier analysis. So you might have something that shows up as this would show up as it's only ever been a low-high outlier, but that doesn't mean it hasn't been insignificant. It just means it hasn't also been a high-high or a high-low or a low-low. It's only ever been one kind of category in the categorizations. So lots of different ways to play around with the data. Hopefully you are as excited about the Spacetime Cube Explorer as we are, because we think it's really going to make a big difference in the usefulness of the cubes, because being able to explore them in this way, I think really just opens them up to really, really understanding the analysis that you've done. And it's going to become more and more important as we build more and more tools that work on the Spacetime Cube, that you're able to really quickly explore them and dynamically explore them in this way. So I promised that I'd point you to them. We have a lot of resources. If you go to esriurl.com/spatialstats, you'll find a lot of our resources. If you go to esriurl.com/spacetimecubeexplorer, right now, that short URL will bring you to our documentation about visualizing the Spacetime Cube. As soon as 1.3 releases, that URL will be redirected to the place to download the Spacetime Cube Explorer. It does require that you have 1.3 to use it, because there's some pieces of code that went into 1.3 that make the add-in work. So with that, we do have a little bit of time we don't actually have time for questions, but we will take some questions. And we have a lot. We have one more workshop today, a whole nother set tomorrow on Thursday, if you want to revisit space-time pattern mining on Thursday. And we hope you have a really good rest of the conference. Thank you. Mm-hmm. Is there a way to get around the requirement to have 10 time periods? There is not, unfortunately. You could do that, yes. You could fake data.
But then your result wouldn't.
If you wanted to, if your whole goal was just to visualize the top 6 time periods or something like that, you don't want to do the analysis, you just want to use the visualization, yeah, you could do that. The analysis would be but the visualization, the parts that really aggregated, would be meaningful.
You can't aggregate with less than 10?
No, I don't think you can create the cube at all. Mm-hmm.
Is there a way to create a requirement that each bin should have a certain amount of data points to make it into the analysis?
There is no way to set a minimum number of features for a bin to be considered valid. No. The only thing you could do, there is a way when you do the analysis to provide an analysis mask, and you could essentially figure out where you had bins that had lower than that threshold, and then you create a mask yourself that masked those locations out. So you could do that if you happen to be a Python developer. Uh-huh. Sure, yes. There is definitely bias around the edges. There's bias around the edges of basically everything you do ever. We don't have any sort of edge correction stuff going on. That is part of the reason that we went with the requirements that we did for like filling in empty bins. We started with a particular number, but we realized that at that number, the edges would never have enough. So we expanded it a little bit, but bias at your edges is it is a problem, yeah. So one thing that you could think about is, one thing to consider is essentially only using kind of things on the interior. Either extend your area, like either get more data outside of the study area you care about, or shrink your study area where you actually consider the results as valid as you'd like them to be, because then you essentially use the edge as neighbors for the interior, but not as part of the analysis itself. Mm-hmm.
On your, when you were doing the spatial analysis, did I hear you correctly? The drop down for the temporal stuff is fixed, like you have to choose a year or a day or a month, or can you customize that? I'm looking at this for visuals for court cases, so it provides problematic if it says 1 year and I'm looking at the month of August over 12 years, because an attorney will tear that apart on cross-examination. You know what I'm saying? Maybe I'm not explaining it right.
I mean, it goes, seconds is the smallest increment.
Right.
And you can say anything between 1 second and 1,000 years and anything in between.
I guess I'm not, okay, you guys looked at the month of August only, over 12 years. So you selected 12 periods and then 1 year. Do you see the disconnect between 1 year of 12 years of August versus a year of January to December?
Sure.
And so if I take the documentation printout into court, a cross-examining attorney is going to tear that to shreds.
Yeah. I mean,
You can use the software right. This says
Right.
Explain that to a jury.
Unfortunately, that would ultimately have to be something that you'd add to however you're presenting the results of that analysis to show that the input data was just Augusts and that the cube essentially represented just Augusts. But there is nothing that you can do from kind of an automatically spitting it out way that would do that. Mm-hmm. So you could, now that would, the question is if you were missing August, could you also do something where you actually use July and September to fill in the Augusts? That would actually be something that really what you'd want to do there is a pre-processing on the raw data. And we've thought about doing something, creating like a sample script that would do that, like an impute values kind of sample script where you just essentially do exactly what we're doing with the temporal, but doing on your input points essentially, where the point itself is what you're like that. But yeah, there's no way to do it kind of out of the box. We are using what is the name of the method we use to, I think it's in the doc. I'm pretty sure we document the name of the method that we use to interpolate along that time series. So you could use that same method, and it's implemented in like R, that you could use to do an imputation before putting those values into the space-time cube. That's what I would recommend in that case. But yeah, that would be a good idea if you knew that you were missing some Augusts at individual locations, because that's the other thing. We're only imputing when the whole bin has no data. So if 3 farms fell in there and only one of them didn't have any data, we're not doing anything about that. And that's really where you have to think about your input data. And that's, I mean, that's just, yeah, I mean, you always have to think about your input data, but it is a really important thing to think about. It's a really good point. Mm-hmm.
Are you going to create a new regression tool?
There's definitely opportunities to think about using the space-time cube and the idea of like a temporal, like creating temporal lag variables and that sort of thing. The problem is, I think it's going to work better when we have a data structure. One of the things that's on our list is to create a data structure that has fixed locations where you don't have to aggregate, but the features themselves stay fixed, and we just acknowledge the temporal nature of them. It's like it's essentially like a space-time cube that's for panel data, where we're not aggregating, and then it would make a lot more sense, because then it could be your counties over a 20-year period, and they have all this other attribute data associated with them. With the cube, now we could put some attribute data into them, and you could geo-enrich a cube if you wanted, in theory, but now let's say you have 10 years worth of data. How do you, at what point, if you have 10 years worth of data, do you have each of the 10 years worth of data that you could geo-enrich into these kind of these cubes that aren't census shapes at all? I mean, it gets very complicated very quickly to do that kind of analysis on a space-time cube, but when we move towards, not move away from this cube, but when we add a new structure that complements this, that's for panel data, I think we'll be a lot closer to being able to do stuff like that.
That could be a location by a polygon.
Yes, exactly. Exactly. And that would be amazing. It's on our list. It's actually pretty high on the list, actually. What's that? Uh-huh. Yeah. Mm-hmm.
I have a question about the NetCDF data format.
Yeah.
That's going to be rolling any other tools out to make access to
So there are some tools. There's a lot of work being done to make dealing with multidimensional data easier in ArcGIS. There's work being done by the raster team. There's work being done to expose NetCDF through Mosaic datasets, which is really powerful. I don't know if you've explored Mosaic datasets at all, but that's one really great way to visualize NetCDF data. And hopefully this Spacetime Cube Explorer, which right now is very specific to our Spacetime Cube, my vision is that it will expand to be a little broader than that, and I'd like it to still recognize, oh, I'm looking at a space-time cube that was created using the space-time pattern mining tools, but it should also be able to say, oh, it's not created by space-time pattern mining tools, but I can still figure it out and visualize something. And so hopefully we're definitely, there's a lot of work being done and a lot of people very passionate about making that happen. So, but I would say if you haven't checked out the Mosaic dataset, that might be one place to start. Okay, well, we have a couple minutes before we have to do our regression analysis workshop. So thank you guys, we really appreciate it.